to my channel. In today's session, Solve With Me, we will find the solutions of previous year's questions of CBSE board examination. So today we have chosen 2 years, that is 2019 and 2018, and we will solve the questions of chapter 1 and chapter 2, that is unit 1. First of all, we will discuss 2019's board paper, CBSE board paper, where the total number of questions was 4. 1 question from section A, that is for 1 mark, 2 questions from section B, that is for 2 marks, and 1 question for section C, that is for 3 marks. So the total weightage given for unit 1 was 8 marks. First question. 2 metal spheres A and B kept on insulating stands are in contact with each other. A positively charged rod P is brought near the sphere A as shown in the figure. The 2 spheres are separated from each other and the rod P is removed. What will be the nature of charges on spheres A and B? This is a 1 mark question. Here we have 2 metal spheres A and B, which is initially kept in contact with each other. A is in contact with B and they are mounted on an insulating stand. Okay. Now when a positively charged rod is brought near A, due to the phenomenon of electrostatic induction, all the negative charges get accumulated closer to this positive rod, and all the positive charges get accumulated farther to this positive rod, that is on the other side of B. So initially, if they are in contact, all the negative charges get accumulated in the left of the A due to the presence of this positive rod, and all the positive charges get accumulated on the right of the B, metal sphere B, again due to the force of repulsion. Now the question is, if you are removing this rod, P is removing, and you are separating A and B. So if you are separating A and B, that is they are not in contact, and you are removing the positive charge P, what happened is that these negative charges get redistributed on the sphere A and the positive charges get redistributed on the sphere B. Now the OR question for the first question. A metal sphere is kept on an insulating stand. A negatively charged rod is brought near it. Then the sphere is earthed as shown. On removing the earthing and taking the negatively charged rod away, what will be the nature of charge on the sphere? Give reason for your answer. Here it is given that a metal sphere is mounted on an insulated charge. One end is grounded and a negatively charged rod is in contact, not in contact, is kept near this metal sphere. Okay. Now when this negatively charged rod is near the metal sphere, due to the process of electrostatic induction, all the positive charges, that is the charges opposite to the negative charges, get accumulated on the left of the metal sphere due to the force of attraction, and all the negative charges get accumulated towards the right of the metal sphere due to the force of repulsion. Now here it is grounded. As it is grounded, Earth is known as a bank of electron. There is a higher concentration of electron in the Earth. As a result, electron always moves from the metal sphere to the Earth. All the electrons moves to the Earth. All the electrons are collected from the Earth. Now when you remove the ground and when you remove the rod, all the positive charges get redistributed in the surface. Since it was grounded, all the negative charges moves to the ground, all the electron moves to the ground, and the only remaining charges are positive charges. When you remove this rod, these positive charges get redistributed on this surface, metal surface. As a result, the charge of the metal will be positive. Finally, the charge on metal is positive. A 2 mark question. The figure shows a network of 5 capacitors connected to a 100 volt supply. Calculate the total energy stored in the network. Here there is a figure of 5 capacitors, combination of 5 capacitors, which is connected to a 100 volt power supply. Here you have to find the total energy stored in this combination. So according to the equation of total energy, Q is equal to half CV square. So V is given in the question, it is 100 volt. So in order to find the total energy, initially you have to find the equivalent capacitance of this figure. So we will find the equivalent capacitance. It is clear from the figure that 3 microfarad and this 3 microfarad, they are connected in parallel. So if two capacitors are connected in parallel, the total capacitance will be the sum of the individual capacitances. So C1 is equal to 3 plus 3, which is equal to 6 microfarad. So total capacitance of this combination is 6 microfarad. Similarly, 2 microfarad and 1 microfarad. Again, they are connected in parallel. So C2 is equal to 2 plus 1, which is equal to 3 microfarad. So the capacitance of this combination is 3 microfarad. Now C1 and C2 are connected in series. So 1 by C3, that is the equivalent capacitance of C1 and C2 is 1 by C1 plus 1 by C2, which is equal to 1 by 6 plus 1 by 3, which is equal to 3 divided by 6, or C3 is equal to 6 by 3, which is equal to 2 microfarad. So the resultant of C1 and C2 is 2 microfarad. Now this combination and 2 microfarad, again they are connected in parallel. So here the equivalent capacitance will be equal to C3 plus 2 microfarad. C3 is 2. So 2 plus 2, again it is 4 microfarad. Substitute the value of equivalent capacitance in the above equation. Instead of C, substitute 4 microfarad. Instead of V, we can substitute 100. So the equation becomes half into 4 into V square. So it is 100 square. So this equation becomes 2 and 4 cancels. So it is 2. This is equal to 20,000 microjoules, or it is 2 into 10 raised to 4 microjoules. So energy stored in a capacitance in this combination of the capacitance is 2 into 10 raised to 4 microjoules. Convert it into SI unit. So here it is microjoules. When I am converting it into joules, it is 0.02 joules. The next question is a 3-mark question where it has 2 parts. Where the first part is to explain briefly using a proper diagram the difference in behavior of a conductor and a dielectric in the presence of external electric field. Second part, define the term polarization of dielectric and write the expression for a linear isotropic dielectric in terms of electric field. Here, the first part is the behavior of conductor and dielectric and the external electric field, where I already did a detailed video. So I will provide the link in the description box below. Now for the second part, what is meant by polarization? Whenever you are keeping the dielectric in an external electric field, a dipole moment is induced in the electrons or induced in the charges in the dielectric, and that phenomenon is known as polarization. Now for the linear isotropic dielectrics, the dipole moment P is equal to chi E into E, where chi is the susceptibility of the dielectric medium and E is the electric field inside the dielectric. For a linear isotropic dielectric, the dipole moment P is equal to chi E into E. Chi is the susceptibility and E is the electric field inside the dielectric, where E is equal to E0 minus EP. E0 is the external electric field and EP is the electric field due to polarization. In 2018, there were only 2 questions, that is 1 3-mark question and 1 5-mark question. So the total weightage was 8 marks. The first question is a 3-mark question. 4-point charges Q, Q, Q and Q are placed at the corners of a square of side A as shown in the figure. Find the first part, the resultant electric forces on a charge Q and potential energy of this system. Here is a solution for the question. we are going to find the force experienced by the charge which is kept as C. This force or this charge experiences a force due to plus Q which is kept at A, and Q kept at D, and this Q kept at B. So, force due to Q at D is FdZ which is along DZ. Force due to Q at B is FBZ which is along BZ. So, the resultant force is Fr. Here we will find the resultant force Fr is equal to root of FdC square plus FBC square plus 2 FBC cos theta. According to parallelogram law of vectors, the resultant force is root of FD square plus FB square plus 2 FBC cos theta. Here theta is 90 degree because you are considering a square. As a result, cos 90 is equal to 0. So the last term becomes 0. Now here we will find the force experienced by Q on the Q which is kept at C. It is K into Q square divided by 2A square. According to Coulomb's law, the force is equal to K into, that is 1 by 4 pi epsilon 0 into product of their charges divided by square of the distance between them. Here the distance between Q and Q is root 2A. Root 2A is the diagonal of the square. Square of root 2A is 2A square. Similarly, we will find FDC and FBC. Both are having the same magnitude, and the answer is KQQ divided by A square. K into QQQ divided by A square. This value can be substituted here. So the equation becomes 2K square Q square divided by A raised to 4. And this becomes KQ square Q square divided by A square root 2. Sorry, KQQ divided by A square root 2. So this is the resultant force. The total force will be FAC plus the resultant force. That is KQ square by 2A square plus KQQ divided by A square root 2. So this is the resultant force. This can be simplified by taking KQ and A square outside. This is the answer, or how to find the resultant force experienced by equivalent force experienced by a charge which is kept at the point C. Here is a solution for second part. That is, we are going to find the potential energy of the given system of charges. So total potential energies will be the sum of all potential energies of that system. So here we have to consider the whole charges, that is whole charges placed at each vertices, and we have to find the potential energies and find the sum of all potential energies. So if I am considering this charge Q, it may experience a potential energy due to Q at D, capital Q at C, and small q at B. So equation for potential energy is 1 by 4 pi epsilon 0 magnitude of the charges, product of the magnitude of the charges divided by distance between the charges. So K into QQ divided by A, this distance is A, plus K into these two charges, QQ divided by A plus these two charges, that is K Q square divided by distance between A and C is root 2A, plus here I am considering the charge at D. This charge may experience a potential due to this Q. We already wrote it. This charge may experience a potential due to capital Q. So here is the expression for that. And this charge may experience a potential due to small q. That is K Q square divided by root 2A. So here we considered all the charges. So K Q Q by A. There are 4 expressions. So altogether I can write it as 4KQQ divided by A plus the remaining expressions. KQ square divided by root 2A plus KQ square divided by root 2A. This is the potential energy of the given system of charges. Now comes the 5-mark question. The first part is to define electric flux. Is it a scalar or a vector quantity? And the second part, a point charge Q is at a distance of d by 2 directly above the center of a square of side D as shown in the figure. Use Gauss law to obtain the expression for electric flux through the square. So here is the solution for the first part. First part is to define the electric flux. The electric flux is nothing but it is a dot product of electric field and the area vector over that surface. Or we can write d phi is equal to E dot ds, or electric flux phi is equal to integral of E dot ds. So this is the equation for electric flux. It is a scalar quantity. Second question is to find or obtain the expression for electric flux through the given square. So in order to apply Gauss theorem, here we have to consider a Gaussian surface. Now let us construct a cube. A cube is a Gaussian surface that we are considering here of side D. Here is a Gaussian surface. This is the Gaussian surface which encloses the charge plus Q. According to Gauss theorem, the total flux passing through this Gaussian surface will be equal to the net charge enclosed within the surface divided by epsilon 0. So this is a flux which is passing through this entire cube. What we have to find is the flux passing through the square, which is one phase of this cube. So the total number of phases of the cube is 6. So the flux through one phase will be equal to 1/6 of the flux passing through the cube, because the cube has 6 phases. So flux through one phase will be equal to 1/6 of Q divided by epsilon 0, which is the flux through the square. So this is how you will find the flux passing through the square, which is given in the question. So option for this question: use Gauss law to derive the expression for electric field E due to a straight uniformly charged infinite line of charge density lambda coulomb per meter. And the second part of this question is to draw a graph to show the variation of electric field with perpendicular distance r from the line of charge. And the last part of this question is to find the work done in bringing a charge q from perpendicular distance r1 to r2, where r2 is greater than r1. The first part is to find the electric field due to an infinitely long straight current carrying conductor, where there is a detailed video. The link is in the description box. Find it. The second part is to show the variation of electric field with the distance r. So when you apply Gauss law, in order to find the electric field of an infinite long straight current carrying conductor, the electric field is equal to lambda divided by 4 pi epsilon 0 r into n cap, where n cap is a unit vector. Here lambda is a linear charge density and r is the distance between the point and the line charge. So from this equation, it is evident that it's clear that E is inversely proportional to r. So as r increases, E should decrease. Now if we plot the graph to show the variation of electric field to the distance, since it is inversely proportional, this will be the nature of the graph. E is inversely proportional to r. The third part is to find the work done in order to move a charge q from r2 to r1, where r2 is greater than r1. So according to the equation of work done dW is equal to F dot dr, or I can write this as F dr cos theta. Here theta is equal to 0 degree. The angle between F and dr is 0 degree. So cos 0 is 1. So dW is equal to F dr. This F can be replaced as dW is equal to Q E dr. F is, according to Coulomb's law, the force can be written as Q into E dr. So dW is equal to Q E dr. According to Gauss theorem, the electric field due to an infinitely long straight current carrying conductor E is 4 pi epsilon 0 r. This value here, so the equation becomes Q lambda by 4 pi 0 r dr. Now we'll integrate both sides. So W is equal to q lambda by 4 pi epsilon 0 in by r dr, because we are moving the charge from R1 to R2. For work done, that is q lambda by 4 pi epsilon 0. Integral of r is log r, 1 by r is log r. So integral of 1 by r, which is log r, applying the limit, upper limit minus lower limit, we will be getting the answer as log r2 to base e minus log r1 to base e. So this is the expression for work done in moving a charge from R1 to R2 from a straight current carrying conductor. So that's all for today. We will continue this session in the coming days. Thank you for watching me.